right. So what I talk about is that in order for you to be able to apply deep learning to the problems, what you need to understand and able to apply are you need to be able to recognize the problem. Once you recognize the problems, that these problems has this nature, you see the data, then you can pick the deep learning technique that is suitable for that type of task. Like if you have image data, you have a spatial data. It doesn't have to be image. It can be different types of data. It can be a map. It can be anything that contain a spatial grid. And that should trigger some resemblance of image processing, and it should lead you to the convolutional net, right? Or if you have a tabular like data and then you need to use deep learning to work with tabular data, then you have the feed forward in order to perform different types of things, right? And you will see that a lot of improvement, a lot of advance in deep learning comes from modification of this architecture and combination of these different layers of different types of network in order to achieve certain tasks that it want, that is like the aims of or the objective of the implementation. Today, yeah, today we are going to look at, I would say, the third types of neural network, which has different approach in terms of describing how data are generated and how can you train the model, how can you let the model learn the patterns to map between input and output from the data, right? So in the feed forward architecture, you can see that what you have created is a model that mix the input together and then try to find the path, the association between the input, so that in terms of the combination, it would produce the output that you want. That means that type of architecture is suitable for the tasks like classification, regression, encoding, because it has a forward flow of data. Convolutional net use convolutional operator, and by using that, it is suitable for a task that require, I would say, require the processing in a larger grid. Like the data are encoded in temporal, time, or spatial, or 3 dimension if you have the data that has higher dimensions. So it doesn't mean that the data elsewhere would associate with the data on the other location immediately, right? You need to have certain patterns like in image processing, like in map processing, right? So that is the convolutional net, that it uses convolution operator to remember the types of processing that it need to perform. Maybe you have a modification of convolutional net, or maybe you will pick a research that further extend convolutional net to other things. Like you can use convolutional net to perform computation of one-dimension data as well, like what we are going to look at today. You can use convolutional net to do the task, yes, but the approach will be different. You can use convolutional net together with another mask to generate some types of focus, right? Focus area on the image, which is called the attention. You can perform something like the CNN combination with just an image of 0 and 1, so that it would create a mask. That mask would be something that it need to be learned as well, to emphasize different part of image so that it could capture the part that are important, and it need to be learned together with the convolutional net, right? So that means the modification of CNN would allow you to processing the data that has larger scale, I would say. That it has larger scale, that has a spatial location that are important, that have temporal location that are important, that the sequence are important, the location are important, or maybe the coordinate in 3 dimensions are important, or density. Right. Now we are going to take a look at another architecture. This architecture is different from the previous one. But comparing to CNN, in CNN you are trying to look at different patterns through the mask, right, through the convolution operators. But in RNN, in this technique, the recurrent neural network, you are trying to view the data as the state machine. That the data, that the pattern is generated. The patterns are generated from certain states. And one state change, your result will change as well, right? And that is the core idea of this recurrent neural network. It is a neural network that take in the output or remember what has happened, what it has produced in the last step. It has state. Okay. Now let's compare it to vanilla neural network. Just a plain neural network. You have input layer in red. This input layer was put into the computation layer and produce output layer. Right? You got the 1-to-1 relationships here. Right? This is for the feed-forward network. One set of input produce one set of output. You can extend that. Suppose that now the network has state. That means if you put in different input or produce output, the state will change. You can have a system that put in one input, like image, and then the model will generate output on each step of the state change. And that you have something like image captioning, that one input going into the model, it has to produce multiple output, right? That contains a sentence, a sequence of words. Actually, there are many generative model that is built on deep learning, so that the deep learning would learn to generate art from by itself. Actually, it was trained based on a certain patterns, and then you give in some types of stimuli, some type of a stimulus, like one word like car, and then it generates the design of the car, for example. This is for something like image to sequence, the image captioning. If your input is a sequence of words like this, multiple words, and output is only like one class, you got a model that is mapping between a sequence of data into just one output, right? And for example, this model can be the sentiment classification model, which receive a string, a sequence of tokens, and then it classifies these tokens into sentiment, whether this is positive or negative. If your model can receive multiple input and produce multiple output, now you have an interesting model that you can be trained to perform something like machine translation, because the model can now remember patterns or decode the data and then encode the result, right? You got the decoder part and encoder part to produce the result. And this is a type of model for the machine translation. And lastly, you can have model that for each input, it need to produce an output. Right? Each input produce output. For example, in text processing, a model like that is a model that trying to tag each word, whether it is the name or not, or the location or the time or not. Right? It would trying to recognize each word, whether it belong to that type of class, whether it belong to the name entity part or not. Or in video classification, that for each frame, the video try to detect certain change in scene so that it can trigger the cut. Right? This is an example here. So you can see that there are different applications that you can use RNN or type of model. I don't want it to limit you to just RNN. Right? When we are talking about RNN here, think about RNN as models that state can change by time, right? That means if you look at papers and you see any papers, it doesn't have to be RNN, but it has a certain, if those model has features that the state of the model, the parameters of the model can adapt through multiple sequence, then it indicates the nature that looks like what we have seen here. And that means you can use those type of architecture and then apply it to perform the tasks that are related to sequence. And when they are related to sequence, you can use it with the time series data, with the time related data. Right? So these are the model in the umbrella of the recurrent neural network. Right? It is a model that you can train the sequence data and then perform different tasks. In the previous deep learning related class that you may have learned, well, you can see that build RNN is not that difficult, right? But in terms of research aspects of this, if you are deciding to pick this as your research topic, I would suggest that trying to look for some advanced technique that evolve the state of the network. It can be the CNN with evolving state, that would be nice, or other type of model, like Boltzmann machine, for example. All right, now let's take a look at the basic vanilla RNN first. What is RNN? Okay, and how does it compute? Think about the green box here as the neural network that we have. Okay, it contains the function that receive input and produce output. Right, we have input x as a vector. This input x is fetched to this RNN. This RNN will receive it as this. That is, you put in the model as input x here. It also needs another input. Think about this as ht-1. It is the state at the time t-1. That means it remembers the previous state and then use those previous state as input to compute the next state. All right. Then we have two input that need to be computed together, and you have the theta. Theta indicates parameters in the model. Right. You have like the weights of the parameters of the model. These weights can be represented as matrices that you will see later on. And then by computing this function, you get the ht. Ht would be the next state. Okay, this type of notation is simple, but it's hard to understand. So we need to kind of unfolding it so that you see it a lot clearer. So from this one, it can be unfolded to be something like this. Suppose now that we also unfold input into a sequence. You have a sequence of input xt-1, xt-1, and in combination with ht-1 are used to compute ht. Okay, and this ht in combination with xt are used to compute then the ht plus 1 and so on. That means for the state t, it relies on for the state t, it relies on ht-1 and xt-1, and ht-1 rely on ht-2 and xt-2. So when you unfolding everything, you can see that at a certain state, these would rely on the previous input and certain function. Right? It's kind of accumulation of the results of the previous input. Or when you kind of folding them, it will be like f of ht-1. Right, of the previous state and the current input, right? Previous state and current input to get to ht here. Right? I should draw something here, right? Something like this to compute the ht. Okay, so this basically extend from just using xt to compute the layers, to use both xt and the previous value of the previous iteration, of the previous state, right, to compute the value here. Okay. So this state value you can think of this h as just a vector. It is just a vector of state, and this vector of state can change, right? It represents the state of the computation. I will have a more elaborate explanation later on here. But what I want you to see here is that the current state is computed from the previous state and the current input. Okay. So what we want is to predict a certain vector at a certain time step. Okay. In order to do that, we need to process vector x in a recurrent manner. So this is the explanation of the whole thing that we saw earlier. We got the new state. This is a function with parameter w. This parameter w will combine, will be multiply, combine with will be used in computing this ht, right, by using the old state and the xt, which is the input of this time step. Okay. And this fw should be known that this fw is used repeatedly throughout the computation. That means the w will be used for the first slice of input, the second slice, the third slice, and it will be used throughout the sequence. And in training, these are the parameters that need to be trained. Okay, so let's look at vanilla recurrent neural net on how it works. Okay, so now we have this first fw, right, and that receive this ht-1 and xt. Now, in order to illustrate it, f here is transformed into something like the activation function, and for this activation function is the hyperbolic tan. Okay, the hyperbolic tan, and the computation inside is the multiplication of the weight. But what types of weight need to be used here? Think about ht as a vector. It is a vector, just a certain vector that you need to vector in one dimension. And WHH, right, when you multiply, say this vector is 1 times 10, and this is 10 times 10. When you multiply them together, you get the vector of the size of 1 times 10. 10 times 10 multiplied by 1 column, 10 row. It should be 10 times 1, right? But 10 row, 1 column. And then you get the size that is the same as ht. Okay. And this, you got the size of xh multiplied by x, which give you the size of the same as ht. Well, I would draw it like this, so to make it easier to understand. For example, suppose that we have like 10 state that we use in this one, right? This h will be the size of 10 times 10 for the first w, and the state h will be 10 times 1, and 10 times 10 times 10 times 1 equal 10 times 1, right? And for this, let's say that xt, x has the size of 5, right? 5 times 1. Then what should be the dimension of wxh? Can you tell me? Put it in the chat, because it is on my head earlier, but because of the cat emergency, I forgot. What should be the dimension of wxh? That the results of multiplication results in, say, 10 times 1. 10 times 5. Correct. Let me put it here. All right. Okay. And why? And for y, because it has to transform from ht to yt, right? It need to have a certain transformation matrix, why. Right. Now you can see that the recurrent neural network has 3 matrices, right? State transition matrix. These are the name that I just it just come out to my head based on the behavior. State transition matrix, input transformation matrix, and output transformation matrix. Right? These are their behavior. WHS is the state transformation. WXH is the input transformation, and the WHY is the transformation from the state to the actual output. And these 3 are needed to be learned. Okay, so these are the parameters of the model that need to be learned. Okay, I suggest that anyone that are interested in RNN and want to understand more about sequential model, take a look at hidden Markov model. Hidden Markov model also has state transition, output transition. Yeah, but it lacks of the input transition. But it has like input, the way to model input. But in any case, those are the machine learning model that is not a part of the deep learning. But well, understanding the larger context will give you like an insight to different types of model, and maybe you can create one your own. That is a mixture between the deep part of the deep model and the goodness of the machine learning, right? Right. So that's it. Right. This is the unfolding RNN. Like when you unfold it into there is a simpler explanation. I hope it's simple for you though. You got this. Well, this is the summarized one. You got X transform with U. Actually, it's W X hash, and W here is used to transform hash, and V is used to transform to O. This is from the book. The other one is not. That's why you got different notation, but you can see that they are actually the same. All right. So take a look here. We got X. X needs to multiply with U, right? You got this here as UXT. And W will multiply with HT minus 1. WHT minus 1. And plus B, right? B is just some constant values or in an intercept in linear regression, or the bias values. These are needed in order so that model can adjust if the data are not well calibrated. It need to have certain parameters that it used to take care of that to capture like the offset level of the data. So that's for B. And then you get A. A is just some dummy variables that you use them to know that these are the combination of these. And you can then plug AT to the tan-h to the activation function, which can be other thing beside tan-h. It can be other, like when you specify into the keras that you want it to be ReLU, you want it to be sigmoid, and this is what you specify it to, right? So for this one in the book you use tan-h, hyperbolic tan, and you got HT, right? This is the state after computation in combination of input and the previous state. And in order to compute output, then you need to multiply HT with V and C, right? And add C here. You got the output. Then you can compare output to the actual Y to get the loss function in order to optimize the model, right? So this is how the loss is calculated. And as you can see here, that if you want just one output here, say you are creating a classification model and you want it to just classify the sequence into label, that means the label will be the output will only occur at the end of this computation. It will occur at the end, and usually this output, the output vector, will be plugged into a fully connected model. We will plug into a fully connected model to perform classification. We will look at that next time. Next time we are going to look at auto encoding, right? And like it is a technique that you can train neural network so that it can produce its own values. That means it need to kind of compress the data down and then produce the same output. We will learn about that next time, and also the concept of embedding, which rely on something very similar to that. Okay. Right. So this is RNN. RNN work in a sequential manner like this. We have H0 and X1 compute, then we get H1 and X2 together, we get H2, and so on until final values. And for each of these, the same matrices, matrices because there are 3 matrices, right, were used to transform data, were used to transform the state and the data, and in combination of those. Okay. Now for the output, can be many to many like this, and you get multiple loss, and combine them to get in combination of loss. Or it can be something like this, many to one mapping, right? That you input multiple x to the model, multiple x to multiple state, and then let the model just produce one output at the end. This is many to one, right? This is often used in say the frame by frame analysis. For this one is for classification, for anything that you want to reduce the data rate. Right? Think about it. There are many models that you want to make decision: regression, classification, estimation, detection. You want those type of model, you want to reduce the data rate, so that at the end you got just one value, right? One class. While some model, you want it to make decision for every instance, and in some model it can be one to many. You want to just give it just one thing, and then it produce multiple output here. Like just give it one word, and then it will complete the sentence for you. So you can guess that the model, like the thing that you type into Google, and then you get the list of the results that is actually come from the model that put those lists there. Or you can attach it together to get something like many to one state, and then you get the one to many, and these two have separated weights, separated parameters, so that it would learn different tasks. Right? If you decided that the model should have the same weight, that would mean that the task is just one task. But in the real life situations, the model might need to do separated tasks, and that means it need to have an ability to learn different things. And then now you can see that for neural networks, many times you are trying to create an architecture that allow the network to learn, right? Just like in CNN, we are creating CNN so that it can detect feature at multi-level, at multi-resolution. In RNN, we are creating a model that can evolve by time, and that can transfer the state so that it can be used to as input, as something that used in computation on another one. Like this one, the HT here is transferred to the next part, the encoding part. The decoding part, the encoding part is the state of the encoding part is transferred to the decoding part and produce output, right? Okay, so let's look at some example here, shall we? We have this a character level language model. We want the model, the recurrent neural network, to remember how to complete complete the word. That is, if we put in some character in, it need to guess what should be the next character. Okay, in this type of model, we would have input just at this hell, actually it's hello, not hell, but O will come at the top. It need to produce that at the end. And this edge will be fetched to the hidden layer, passing through this function, and this will be used to compute together with to compute another one here using with E, with L, and with L, and it need to produce something like this. For H, the supposed output should be E. For E, the supposed output should be L. For L, the supposed output should be L. And for L, it should be O. For if you have like multiple L, the last one should be O. This is how you need to remember that. But there will be errors that occur here. This is like the ideal case, right? But if you compute it here, it can make errors. Like this one, H supposed to be E, right? But well, the highest value here is like this one, right? This for E is supposed to be L, next one, and L is this one. It's not, right? For L, it's supposed to be another L, and it's right. And for L, it's supposed to be O, which is correct, right? Some are correct, some are not. This need to be tried first, but you can see this is how it is computed. Okay. Right. In the test, when we put into the model at each step, actually what we have is just this input H, and then H0, state 0. Then we compute this state to get output, and this output then will be used after computing softmax. Be used as input here again. This for this one we know that this is E. Then we use E as input, and this one we have L. Use L as input. Another L, another O, right? Right, and so this is how it works in the language model. We need to kind of, in the training, we need to use like the subsequent character as output, and let the model learn how it could map at each interval. Okay, how would it learn? Right? It would in the learning phase, right? The model will need to run forward, and then propagate the error back to the input. Okay, that means you need to have forward computation and then backward computation. Okay, that means you need to forward through entire sequence to compute loss, and then backward through entire sequence as well to propagate loss back in back propagation. Sometimes it's difficult to do that, right? So sometimes the loss is truncated, and you can have like truncated back propagation through time, run forward backward for a chunk instead of the whole sequence. Let's say that you have the data in like Wikipedia. Instead of training model for the whole Wikipedia, you can cut it into sentence and then train each sentence. So that is a type of truncated backpropagation, because you are doing it sentence by sentence rather than using the whole thing to train the model. Okay. That means the back part will be truncated. Or you can design a model so that it perform forward and back propagation for each one through time. But let's say if we were to train this model, right, using forward propagation throughout the whole thing, and then doing the back propagation from the end to the beginning, there will be serious problems that need to be addressed, which we will talk about that later on. And that is why Right now, if you were to use the RNN style model, you wouldn't use the vanilla RNN. What you use would be something like the LSTM, right? The long short-term memory, or the GRU, which in both it deal with the problems of vanishing gradient and exploding gradient, which we will take a look at that later on, right? Oh, by the way, for this for assignment, the assignment for this would comes out next week, because to properly work with a sequence model, especially for the textual data, I think you need to understand the concept of embedding first. Right? That would allow you to, instead of using one hot encoding like what we saw earlier, you can then use the embedding vector as input rather than that ridiculous one hot, which will be ridiculously long because it kind of need to capture all the vocabulary, right? But in any case, let's look at this language model for the RNN first. I don't think I prepare the lab for you guys though. I will post the experiment, the lab that you can test out using RNN to build the language model, but that will not be the assignment for you. In the assignment, I will probably ask you to do sequential analysis rather than performing the generation here. This for this one, the experiment would be to create language model that can generate, say, the word that you want, or the whole text. It can write the new text out. Okay, how would it be able to perform? Let's say that you have this William Shakespeare data, right? And then you train the sequence here. You with just RNN. In the first iteration, it will be able to generate like next character out like this. When you train it more, then you get something like this. Train more, then you can see that, oh, some of the words are correct already. And when you train it more, then it can generate something like, why do what that day? What does that mean? Reply Natasha and wishing to himself. And you can see that in a lot of hypes and news that you may have heard, that well, there was an AI that can write its own code, an AI that can write a story, it can write a letter. It comes from something like this, right? So if you are interested in picking those as a research paper for this course, feel free to do so. It would be interesting to see how it's done. Okay. Finally, this is what it can generate. It can even generate what each character should speak. Well, this is interesting. Now let's imagine, actually, you can use different sources of data to train this RNN, and it's fun. You can try it. I will post the notebook that you can try this language model RNN on the book, on Shakespeare. This one, but you can apply it to other things. Like you can say download the data from the Stack project, the open source algebraic geometry textbook, and train the model. This is the work done by the authors that they train this textbook using the model, because it's a sequence, right? And because this is LaTeX, it means that the model should be able to produce LaTeX in the correct manner, and it should be able to produce equations. And this is the result. Look complicated. Certain lemma, and yeah, and well, it has a proof. It has certain thing. I don't know. Maybe this would pass as a paper. Right? Now you have to publish a paper. Maybe you can try this. Let the model publish, write a paper for you. But I wouldn't recommend that. Or you can train the model using the previous paper that you've got from internet, whatever. You can try that out. But well, I will post the link for that notebook to our group, and then you can try it out. Just tweak the code a bit if you want to get the data in. But the result would not be that great. It would be better if you have the embedding vector, and then use embedding to retrieve the word or encode the word. But now the code that I use is only using one hot encoding. Simple one hot encoding. Right. You can use something like this, the code from Linux tutorial. right? Linux, right? Train it with the Linux code, and it produce Linux code. It can generate C code, which I don't know what it does. The do command, right, which will do something. You can try this if you want, right? Just let it learn some GitHub code. Right? You can let's say learn the some GitHub that you clone, and then let it generate the new project from the old one. It's fun, and it even generate this the license from Intel Mobile Communication. Don't know what that is. The program is free software. You can redistribute it. Yeah, it even generate this GNU license declaration here as well. Now, in the application of the RNN, right, you can plug the RNN to different model to get different results. Like if you pair the RNN using the language model with CNN, saying that the CNN at the final state, you can cut the classification out and use it as the initial state, encode it into initial state for the RNN. Then you can create an image captioning model. Now this is the CNN. This part is RNN. Right? Just combine them and let it run. Right, so in order to do that, you got the test image coming here. You need to go through something like the VGG, convolutional net, but you kind of cut the output out and get fully connected to encode the data to some initial state, and then use it to compute H0 and let it generate the output like that. Here's the result of image captioning. Actually, one of your friends, Tanit, you can comment on this, on why it's work, why it's not. Right? And the good examples are like this: that is a cat sitting on a suitcase. It can produce quite accurate output that describe the image. But there is also like the weird explanation that is failed because of maybe because of the woman is holding a cat in her hand, probably because it recognizes the texture. Yeah, on her hands as well. The person holding a computer mouse on a desk. I don't know whether there's a mouse there. Well, the text is correct, but it's wrong. Okay, and for example, this one, the bird is perched on the tree branch. There's no bird here, but because of the background, maybe it kind of put the bird there because of the background, because every bird photo has this blurry butter background that melt away, and you got like the branch in focus, and those are elements in the image that are in the other image, and that's why this is the fail case. Okay, now Tanit, do you want to comment on something about the image captioning and your try out on the undergrad degree, and what are the difficulties on creating these? Okay. So yeah, so what Tanit just mentioned is in terms of the difficulty in order to capture the language in explanation, because in order to do something like this, you need to have a diverse data set. That is, you need to have the data set that contain a quite elaborate explanation. And what we're trying to do in his undergrad level was to create a model that using the data from what tape shop, right? From e-commerce site, and then take in the title and the image, and then trying to match them. The problem is it's not diverse enough, right? But if we are say Shopee or Lazada, maybe we can do that, because those have the internal database and they can definitely train it on the model, right? Or if you think about Facebook has I don't want to use a ton, because it has like a huge a very large data set. It has Instagram, right? It has the image in Facebook, and it also has the post at the description. You can imagine the richness of the data that it can generate out. Although I know that there were like sarcastic posts and others, but just imagine that there are those descriptions together with the data that they can train the model with. So that would be nice, right? Right. So that's the application. This is the application that this is one of the modification of the model known as the bidirectional RNN. You got RNN, the same RNN that compute forward, but there is also a backward path. That is, X is used to compute H as a forward path and compute G as backward path, starting from the end to the beginning, and then both are combined to get output. This is called the bidirectional RNN. Bidirectional RNN is good if the patterns is not causal, right? It's not left to right association. It has a certain lookup at the end to get the beginning. What I'm talking about, right? I'm talking about actually is the human cognition. Many of human cognition contains this type of behavior. Something that is called precognition or that is called prehension movement. That is, before we actually make a move, like this camera, if I were to reach the hand to this camera to grab it, I would not use the same velocity all the way, right? Because I know the distance here. And what I would do would be I would slow down before grabbing it. Right? That's the this called the prehension movement, and this occur automatically in our brain. That in speech, in motor movement, in a lot of things that we use our neural computing, our neural capability with, we have an ability to recognize or guess the future, and then using that information to generate what we should do, what we should say. For example, I know that I need to speak a question. When I speak the question, you can see that I plan the planning of the sentence would be different when you speak with, say, the declarative sentence. Right? That means there are certain things that require looking up, that require computing at the end and come back at the beginning. Okay. And in those type of sequence, in many times, bidirectional model would work better than sequential left to right model. Right? So one of my students used this bidirectional RNN to model the Thai national name entity recognition. Right, to use LSTM, compute forward and compute backward, to recognize whether this is the name or not, or whether this is different types of character. This is location or not location, right? To classify it, whether this is a person, this is a location, for example, to classify each word. Okay, so that is the bidirectional RNN, right? Now let's look at the last topic here. Okay, you have seen the RNN on how RNN work, how RNN can be computed, and the computation steps of RNN. Although I did not actually multiply the matrix to show you that, but just from this equation, you should be able to guess the behavior of the model from this equation. Where is it? Somewhere around here that contain A. Yeah, this one. From this equation, you should be able to guess the behavior of the model already. It's just a matrix multiplication RNN here. Except that you need to do it using the state vector as well, and then state vector would keep something that relates to time, the change through time, the change through the sequence, that would capture the change of the pattern in X, and it would associate with the output here. Right. Now, when you have RNN, you can stack RNN in multiple layers. Up here, you can have RNN and then use the output to be the input as another RNN. And this is the deep learning part, that you can have a deep RNN in a multiple layer here, right? In multiple layer RNN, it would be able to be able to remember more pattern. Like the sequential part here can extract certain feature and then use it as a feature as input to extract another label or feature in the above layer. Okay. Now let's look at this. You can stack RNN. Right, let's look at this problem with RNN, with just the vanilla RNN here. What is the problem? And then we'll come back and talk about LSTM. I have on the slide subsequently to discuss about that. This is the RNN. RNN has input here for each state computation and has HT here. In order to compute, you don't have to separately compute. You can stack them. Stack HT and XT together, or stack them together, and then multiply it with W, right? Multiply with W and put into tan H, you get H here. So here, instead of having two parts adding with one another, you can have the multiplication of this matrix HH and HX and this vector H and X, which when you combine it, it's just W. Okay. Now, what is the problem? In back propagation, right? For it, you need to back propagate. You need to propagate the error from HT back to HT minus 1, right? Back to the previous state for each of the state. The problem is that for each passing through this, it need to multiply with W, right? It need to multiply with W. What does that mean? That means if you have multiple states of computation, it has to pass through multiple multiplication with W all the time. That means W will be a factor that is repeatedly multiplied to the error, multiplied to the gradient. And that creates two problems. The first one, if W has the singular value or the volume of W is more than 1, then multiplying multiple times will create the problem that is called exploding gradient. That means the error is too large because it's multiplied multiple times. W would be like, if W is like 1.2, will be like large value when you multiply through the sequence. Or if W is less than 1, when you multiply 0.9 a number of times, it will eventually reach 0, right? So you can, the above can be sorted out by doing the gradient clipping, meaning that you can just clip the gradient. Right? Clip the gradient means that you can just create a threshold, and if it's more than threshold, then you can clip it to just some value. The latter one requires the change in the architecture, because this architecture does not accommodate the flow of the gradient that well, right? The change is to change from something like RNN into a more complicated one, the LSTM. Okay, before we look at LSTM, let me take 10 minutes break, and let you take the time to kind of clear out and then maybe just look through what you have learned in the earlier class about RNN, because LSTM is quite confusing. I have to admit, it has a lot more part that need to be explained. So let's stop here and take, say, 15 minutes break, not 10, like 15 minutes break. We'll continue on 7:15, right, on the LSTM, and just that is the end of the class. But LSTM is quite difficult, so let's pause, and then after the break we will come back and take a look at LSTM. And by the way, if you have questions about RNN, about also issue related to RNN, put it in the chat. I will come back and answer those. Okay, so let's take 15 minutes break and we'll start at 7:15. Okay, I'm back. Yeah, let's look at the last part, right? This is the left hand side. Here is RNN. Okay, you compute the state based on previous state and input, multiplying with the weight. You got the current state. But you can see that LSTM has a bunch more. Right? It has the computation of the state. It has different gate here. Looking at it like this will be confusing. Let's look at it in the diagram here. We will come back to this one. Well, let's look at the name first, and then we'll come back to this one after looking at the latter slide. Okay, it's easier to look at the flow than looking at just the equation. So F here denotes something that is called forget gate. Right? Forget gate is the gate that will learn whether it need to erase the cell or not, right? And I gate is input gate, whether to write a cell or not. G gate is gate, whether how much to write the cell, and O gate is output gate, how much you need to review it. Right? We will come back here and learn it in backpropagation manner. Okay, this is LSTM, and this is equation of LSTM that we have seen earlier. Let's look at it one by one, shall we? Start with this xt. Xt is input vector at that state. Ht minus 1 is the state from the previous state, right? First, we need to stack them together and multiply with W. This is the same as what we got earlier, but what is the difference? Okay, this combination multiplication, instead of passing through the activation function directly, right, what happened here is that it need to pass through different part, right? First, this output on one part, it will pass through this f. It will pass through this f function, and this f, which is the forget gate, this f will be multiplied with ct minus 1. Well, what is ct minus 1? Think about ct minus the C channel here as the long-term memory, right? This would be something like the long-term state that remember from the previous state, that it kind of remember it long-term. While this one, it has to take care of X. It is like short-term memories. So for F here is the gate that decide whether it will let ct minus 1 pass or not. Okay, and how does it goes here? How does it work here? For f here, f would comes from multiply the delta function with the w h. This is the function. Like we have tan h delta, certain delta function. This delta function will determine whether it will let this pass or not. If it decide that like the earlier memory doesn't really matter. That is, the pattern is just the combinatoric pattern. It's just for this time instance only that is important. Then f would be value something like 0, and then this will be about 0. That's why it is called a forget gate. Okay, because it kind of forced the previous memories to be 0 if it need to forget. Right, that's the first one. Second one is the I gate. The I here is the input gate. Input gate decide whether to remember this or not. Right? Whether to remember this long time or not. Think about it. When think about the gate here, think about it like that it will take the output of multiplication and transform that into the multiplicative factor, right? This can be like 0 and 1, right, for that. If it's 0, then it means forget. If it's 1, it means okay, we will take the previous memory for this one. For the I decide whether you want to commit this to memory or not, because when you look at it this way, I here will be binary, will be whether this is 0 or 1. The gate here is like a buffer that you get here. If this said to forget, then it will be 0, 1. If it's 0, right, forget. If it's 1, then you got the value of gate here, output here, and then multiply by 1 as the output that goes to the addition here. Okay, this means you are committing the computation to memory. Okay, this is the committing computation to memory, and then add it with the previous memory. You got the combination of this memory out. Lastly, this is the output gate, which come from multiplication of the short-term memory. This is the short-term memory passing through O. Then here's the multiplication. Multiplication of what? Is the multiplication of the long-term memory. Now CT passing through tan H, multiply together, and you get HT. Right? HT here will be, if you look at this, the output gate would be the enabler. Again, 0 and 1, whether you want the output here or not, whether you want the output out on this level or not on this level. And then you can see that the flow of the gate combining with CT, you got like the flow of the two parts coming together, and then passing through the activation function to compute HT. Right. This is the long and short-term memory. The RNN with long-term memory and the short-term memory. And think about F, I, and O as on and off, right? The delta here as the as enable or disable, as enable or disable of each of the row, right? F is to enable or disable memory. I is to enable or disable the output from computation. O is to enable or disable the output, right? And then now you can see that this certain now means something, right? You got CT, which come from the multiplication of F and C in combination with I and G, right? I and G here. And then you pass C3 to tan H, multiply with O. You got the result HT. And then for each computation, the HT and CT will be computed out. Okay, now let's look at the previous one here. So this is what it means by this equation. And this is what it means by computation in terms of the matrix. Right? So in this case, in the original RNN, you need to stack the matrix and multiply W with X and H, right? And then once you multiply it, then you get the result passing through sigmoid and tan H. You get the value at each gate, and these are the dimension of those matrices. So how does it help in terms of vanishing gradient? It helps because backpropagation from C to C minus 1 only pass C to C minus 1 only has this F multiplying. There's no W at all, right? That's just enable or disable here. So it means that it can pass through the channel directly from the output to the input. The idea here is very similar to residual, right? ResNet, right? The residual network in the CNN, that you create some types of skipping channel that the gradient can pass from the output to the input to the earlier layers easier. This as well. LSTM is good because it has this channel, uninterrupted gradient flow that can pass from the end to the beginning to the earlier networks. Okay, there are actually an alternative model that works similarly to LSTM. It's called GRU, but I'm not going to look to focus into that. If you want to discuss it in your paper, it's fine, right? It's the learning phrase representation using RNN encoder and decoder, right? Using statistical machine translator. But I would say that because GRU works similar to LSTM, presenting it again would not be that interesting. I would challenge you to find different other types of papers that extend the knowledge further rather than sticking with this. This is like the basic architecture. Let's talk about other things. And there are also other multiplication, this like MUT that also trying to address this problem as well, right? This is actually the end, right? See, it's not that difficult. Right? I need 15 minutes break before the last year because I was kind of at the end of the endurance talking probably. It's like the evening already, and having class in the evening, well, if you have teaching at the university is better in that when I teach I have to walk around as well, and that actually improve the health and endurance in teaching. Teaching in front of the camera is fine, but you can see that if the video is too long and it's boring. If, say 3 hours class on on the camera and on the video you tend to watch on YouTube, that's boring, right? So I will keep it short, and but you need to practice here. I will post the experiment that you should work on your own, maybe building the RNN language model that train it on something. Show me next time if you complete it. Otherwise, next time don't forget to submit the CNN assignment as well. That will be due next time, and also I will give out the another assignment next time on RNN. These are some references if you want to test your skill on. But I will also have the lab experiments if you want to try it on. Right. This is the end of lecture 9. You have any question that you want to ask? Feel free to do so. Actually, at the last year, I tried to be thorough. I even cut one video into a smaller part so that I got multiple chapters, and you can skip through the chapters. Tell you the truth, I don't have time to do that. There are so many things that need to be done. Like the last week video, I haven't encoded it yet. Probably I will upload it in just a Zoom form. Right? I haven't put the work in yet. Not just your class, though. The other class as well. There are other things coming up, and working on editing video is quite a lot that need to be done. And I actually have a stack of reports that need to be written. Yeah, lots of those. Okay. Well, so that's it for the RNN. Okay. If you have questions, ask in the group. I will answer as soon as I can. And if you already pick your paper, show me. I can give you some guidance, whether it's good or not. You can ask whether the scope is okay. Because sometimes if you pick a large paper, a large journal, then it will contain a lot of things that I can point out on the thing that you need to focus on. Or sometimes you pick a very small paper from the workshop. It will focus on just a tiny bit, and you might need to increase your scope. So in that sense, show me those papers first, and I can make recommendations on the part that you need to focus on. Okay. You can find those papers in arXiv. arXiv is peer review, and so you need to be careful, right? There are a lot of good papers in arXiv, right? But there are also a lot of not so good papers in arXiv as well. So picking picking papers from the not peer review source, you may need to be careful about that, right? And there are also other papers from predatory publisher, right? I'll say that those are like a bogus journal, right? So be careful about those. There's a number of them. So you can search whether the paper is reputable, looking at the letters from SciDirect, IEEE, Nature, or you just show me and I can confirm that for you in that sense. Okay, so that's about it for today. Let's go. Right, let's close the session here. Okay, see you next time. Bye bye for now.